Everyone. In this video, I will go over my solution for the problem named LIS or reverse LIS taken from today's Codeforces round. This problem is an excellent problem which combines three important concepts. The first one is the idea of constructive algorithms, in which we construct an array. In this problem, we are not explicitly asked to construct and print a solution, but we are going to do that because the construction will obviously help you see the solution better. And in the construction, we need to maximize some quantity. The quantity which we need to maximize is going to be done greedily, so we will get a glimpse into some greedy ideas as well. And finally, we also get to see the concepts of longest increasing subsequence and longest decreasing subsequence. So in this case, you can see from the problem name itself that reverse LIS can actually be interpreted as a decreasing subsequence as well. And I'll explain that as we understand the problem itself. So let's look at the problem statement. So in this problem, we are basically given an array A of n integers. The LIS is the longest increasing subsequence. You can read about it in the Wikipedia page. And you can see the examples that the LIS of this array is 1, 3, which is 2. The LIS of this array is 3, 5, 10, or 3, 5, 20, or 3, 10, 20, or 5, 10, 20. So there are actually 4 LISs, each of which has length 3. And in the next example, there's only one LIS of length 3, which is 1, 2, 4. Now that's the longest increasing subsequence. And we define an array A prime as the array obtained after reversing the array. So the reverse LIS is actually going to be the LIS in the reverse array. And another way to consider the reverse LIS is to look at the fact that if you take an array, for example, 2, 1, 1, 3, and if you reverse the array 2, 1, 1, 3, then what you get after reversing the array is 3, 1, 1, 2. And if you want to find the LIS of this array, you can see that it's 1, 2. So this is actually the same as the longest decreasing subsequence 2, 1 over here, and that's why you can see from this example and from other examples as well. So for example, if you reverse this array, you get 4, 2, 1, 3, and in that case, the reverse LIS or the longest decreasing subsequence in the original array is actually just one element 3. And in the second example where you reverse the array, the LIS of the reverse array is again only one element. And even in the original array, the reverse LIS is just 1. So the reversing the array, the reverse LIS is just equal to the longest decreasing subsequence of the original array. And the longest decreasing subsequence is exactly the opposite of LIS. So it's just a decreasing subsequence. And you can make out from the name that it needs to be the longest decreasing subsequence, strictly decreasing. And finding the reverse LIS is same as finding the longest decreasing subsequence of the original array. And there's actually a small mistake, I think, over here. This should be 4 because obviously the longest increasing subsequence is 4. So maybe they'll correct that. This is the testing page, by the way. So maybe in the actual page they would have corrected that, but you can see that it doesn't really matter much for the actual solution. But just for clarification, this should be 4 because each element is strictly increasing in this array of length 4. Anyways, let's try to understand how we can maximize the minimum quantity of the LIS and the reverse LIS if we can arrange A arbitrarily. So basically the problem basically asks us to permute the original array, and permute basically means to rearrange the original array such that we are maximizing the minimum of the LIS and the LDS of the array. So we want to convert A into some other array, and we want to maximize the minimum of LIS of A and LDS of A. So that's what the problem is asking us to do. And let's try to look at some examples and see how exactly we can maximize the minimum of these two quantities. So in the first example where we have all elements equal to each other, so those are all just 6s, then obviously however you arrange the array will remain the same, and that's why we can just consider the LIS. So LIS is equal to 1, and the reverse LIS or the LDS is equal to 1. So we just print 1. In the second example, when we have the array let's first sort the array, because sorting is always a good idea whenever you encounter problems where you need to maximize the quantity corresponding to increasing and decreasing subsequences. So once you sort the array, you can see that this is the sorted version of the array, and now we want to change this sorted version of the array into a better one, obviously, because in this sorted version of the array, the LIS is maximized, that's for sure. The LIS is just 3. However, the LDS is actually 0, I mean 1, because obviously if you keep all the elements strictly increasing, then when you reverse the array, they won't be increasing, or basically when you consider the decreasing subsequence in the same order, there won't be a decreasing subsequence, which is why just sorting the array won't work. So although this is a good idea, in this case it won't work. So let's try to modify this, and let's try to basically see exactly how we can permute the array to make sure that both increasing and decreasing versions happen. So in order to ensure that the array is increasing and then decreasing, we'll try some construction. So this is where some constructive ideas come into the picture. We want some construction such that we are increasing first and then we are decreasing. So this type of construction is called a mountain type of construction, where you want the numbers to be increasing and then decreasing. So you can view this as a palindrome or as a mountain, which increases in height and then decreases in height. And in this case, you can see that both the normal way and the reverse way, we are getting the same LIS and LDS of 3, and the LIS is 3, LDS is 3, which is why this construction gives the correct output of 3. And now a key observation arises that if the array is palindromic, if it's perfectly palindromic, if each element appears an even number of times, or if you can make it a palindrome, for example, if the array is something like this, and you can sort it and make it a palindrome like this, then obviously this is the best construction. So this is the target construction which we are going to try and make, and intuitively this should be clear why this construction will prove to be the best, which will prove to maximize this function, and the reason should be clear, that it will both increase, and it will increase in both ways the longest increasing subsequences, and that's why we should try to make it as palindromic as possible. However, as you can see in the third example, it's not always the case that the array will be palindromic. It could be possible that the array consists of numbers like this. So in this case, it won't be optimal to it won't be possible actually to make it palindromic, because 1 and 1 are not the same on either side. And if you just consider this array in the sorted manner, then obviously the LIS is 3, but the LDS is 1, and hence the minimum of 3 and 1 is 1, so this is not optimal. However, there is no other optimal, there is actually another optimal solution, sorry. The other optimal construction which will give us a better result is this. So in this case, you can see that 1 to 3 is increasing, and then 2 to 3 is also increasing in this way. So that's why the LIS is 2 and the decreasing subsequence is 3, 2, which is also of length 2. So this construction proves to be optimal and gives us the maximum possible beauty of 2. So these are the 3 examples, and now let's try to find out a construction which will greedily maximize the function taking into account that not all inputs will be palindromic. So let's try to find out an algorithm which will try to maximize this function. So we need to approach the construction using frequencies of elements, because we can analyze the frequencies of elements and come up with a number of cases. So let's see how we do that exactly. So we can analyze the frequencies by noticing that if we have some number x which has a frequency greater than 2, then it actually doesn't matter what the frequency is as long as it's equal to or greater than 2. The reason why the numbers with frequency greater than or equal to 2 are all similar is because if the number x is there such that its frequency is 2 or greater, then you're going to place one value of x, one occurrence of x in the LIS over here. And so if you consider two parts of the construction, there is an increasing part and then there is a decreasing part, and the decreasing part actually becomes a reverse LIS. So that's why in the two parts to the construction, you're going to basically have at most like in each part of the construction, the LIS will contain only distinct elements and the LDS will also contain only distinct elements, because that's the definition of the LIS and the LDS, that they are strictly increasing or strictly decreasing. So because they contain only distinct elements, the numbers with frequency 2 or greater, one occurrence will be placed in the LIS and one occurrence will be placed in the LDS. So that's why a simple idea is that if you let count represent the number of elements with frequency greater than 2, then the LIS and LDS, the length of LIS and LDS will be at least count, and hence we know that we can just put count elements in the correct order in the LIS and the LDS, and it's done. However, if there are frequency greater than or equal to 2, if the frequency is 2, then also we can put one in the LIS and one in the LDS, and we are done. However, the problem arises when there are elements with frequency only 1. So let's represent count frequency 1 to be the number of elements with frequency 1. And if you consider count frequency 1, then it isn't clear which side should the elements go to maximize the minimum of the two quantity. And the key idea is that you should actually place the elements in alternating fashion. So you should place one element in the LIS, one in the LDS, and so on alternatingly, so that it's almost evenly distributed. So for example, if you had the numbers 1, 2, 2 and 3, then it's clear that 2 will belong in the LIS and the LDS. So you'll place 2 over here and over here. However, the other one, which is basically 1 and 3, you're going to place 1 over here and 1 in the other side, in the opposite side for the LDS. And in this manner, you're going to be able to maximize the LIS and the LDS. And hence so this is the LIS part and this is the LDS part. Hence, by placing the 1 in the beginning and in the end, you are both maximizing the LIS and the LDS. So you are placing 1 on the left half and 1 on the right half. By 1 I mean the numbers with frequency 1. So by placing the elements with frequency 1 evenly distributed on the left and right halves, you're simultaneously maximizing the LIS and the LDS, and in that manner you're ensuring that the minimum of the two will be maximized. So let's try to find an expression just using count and count frequency of 1. So as I said, the answer will rely on the fact that count elements will belong to both sides. So you're going to add count to some quantity. Now in the normal case, when count frequency 1 is exactly 2, it's exactly an even number, then we just divide them evenly into both halves. and in that way we are maximizing the LIS and the LDS. However, if count frequency 1 is an odd number, then it turns out instead of taking the floor value, which is the lower value, you have to take the ceiling. So you actually have to do this thing to take the ceiling. And the reason why we do the ceiling is there are two ways to write this. You can either write this as the ceiling and use doubles, or you can just do this, and this basically makes sure that you're taking the ceiling of count frequency 1 divided by 2. The reason why you take the ceiling is because there can be one element which is part of both the LIS and the LDS. So in both the LIS and common to both LIS and LDS, there cannot be more than one element, because obviously like the largest element can be common to both, the other elements cannot be common to both. So that's why there can be one element common to both LIS and LDS, and hence we are essentially just making the use of that common element. So you could either write it as the ceiling of this. So this is one way to write the expression, and the other way to write this expression is you remove the element which is common to both, and then you take the floor of the remaining. So then you take the floor of the remaining, which is essentially the same as doing this. So both ways, either explicitly saying that you're keeping one element common to both LIS and LDS, and then you're taking the floor of the remaining elements, or if you just use the fact that in case the number is not even, in case it won't be evenly distributed to both halves, then only you will keep one element common to both LIS and LDS. So this way is better. Like this way more accurately conveys the fact that only when the number of elements with frequency 1 are not evenly distributed between the two halves, only then you can take the ceiling. So that's why I advocate that you take the first expression and you just keep track of how many elements have a frequency greater than or equal to 2, how many elements have a frequency of 1, and then it's just a one-line code which sums up these two quantities. So now I'll just show you the code which implements the same idea. So in the code for each test case, I taken the value of n. I use the frequency map to store the frequency of each element. And note that the construction is not explicitly given, but you can see that essentially we are taking take all elements with frequency 1, take all x such that frequency of x is 1, and distribute them, divide them evenly into LIS and LDS, and hence basically count frequency 1 divided by 2 ceiling plus count will be the answer, because count frequency 1 represents the number of elements such that frequency of x is 1, and we are also taking all y such that frequency of y is greater than or equal to 2, and putting them into both LIS and LDS. So the number of such y is given by, because x is given by, number of x is given by count frequency 1, and number of y is given by count, and hence once you just do the loop through each element, so this goes through take each element in the map, and num represents the element, num is the element, and this is the frequency, and if the frequency is 1, we increase count frequency of 1 by 1, otherwise we increase y by 1, because frequency will be greater than or equal to 2, and hence in the end we just print the value of x plus 1 over 2 plus y, because y represents the elements which are put in both halves, and x plus 1 over 2 is essentially the ceiling of count frequency 1 by 2. And so I hope you got the construction and why this greedy idea of distributing the frequencies evenly into both halves when the frequency is 1, and when the frequency is greater than or equal to 2, putting them into both sides. one occurrence each, why that construction works in maximizing the LIS and the LDS. So I hope you got that construction. And if you have any doubts in any part of the solution, do leave them in the comments down below. Thank you.